With each entrancing picture caught by the James Webb Space Telescope, it continues to gather thought from different corners of the universe, including planets inside our own planetary system. A year sooner, we considered our most significant brief look at pictures showing the Carina Cloud, the Sox Quintet, and, strikingly, the spellbinding Deep Field picture. This unequivocal picture obviously portrays various galaxies resting in the immense scope of the universe, fulfilling the suspicions made. The James Webb Space Telescope hasn't quit being a labyrinth. It has revealed objects that challenge deep-rooted cosmological speculations. These dumbfounding discoveries are now being named universe breakers by cosmologists, baffling established specialists with their ability to challenge existing thoughts. The explanations for these discoveries remain covered in secret, tossing our hypotheses and theories into chaos. So, what's the most recent scoop from the James Webb Telescope? What exceptional new revelations has it uncovered that were previously obscure to us? Join us as we dig into the discoveries of how the James Webb Telescope has introduced proof suggesting the presence of another universe, testing the standard understanding of the Big Bang. Our universe, as we've long perceived, rose from a hotter, denser state by means of a hypothesis known as the Hot Big Bang. This idea, a significant scientific accomplishment over the course of the past century, gained overwhelming support during the 1960s with the discovery of the cosmic microwave background, CMB, an echo from the early hot and thick state. Over time, the Big Bang has remained the predominant theory explaining the origins of our universe. In any case, new and basic observations have driven cosmologists and astrophysicists to reevaluate both the continuous expansion and the Big Bang itself. Despite these difficulties, alternative speculations have failed to build up momentum, with the enduring nature of the hypothesis of the universe's starting point continuing. According to the common view, the universe's origin involves a smaller, denser universe in the far-off past. The presence of radiation, like photons, indicates that the universe was hotter at its beginning and has since cooled. Extrapolating backward in time, the density, temperature, and energy levels arrive at a point where a singularity could form and regular laws of physics break down, around 10 to the power of minus 43 seconds. In such a brief range of time, small distances, brief time scales, and high energy levels challenge our comprehension. Rewinding the cosmic clock to the theoretical 0 point, if the universe began as hot and dense, it would have expanded and cooled, producing vast numbers of particles and antiparticles, with excess particles annihilating each other via radiation. As temperatures decreased, the breakdown of the weak and Higgs forces led to the development of the four fundamental forces and particles with non-zero masses. As the universe cooled further, protons and neutrons formed composite particles called quarks and gluons. The combination of protons and neutrons led to the formation of light nuclei, such as deuterium, helium-3, helium-4, and lithium-7. Overdense regions went through evolution due to radiation pressure, followed by gravitational collapse, leading to the formation of large-scale structures. Around 380,000 years after the Big Bang, the universe cooled enough for stable neutral atoms to form, marking a crucial step where photons decoupled and their wavelengths stretched as the universe expanded. The discovery of the cosmic microwave background many years ago cemented the theory of the Hot Big Bang as the most supported explanation for the universe's creation. Big Bang versus steady-state theory. While most cosmologists and astrophysicists embrace the theory of how things came to be, resolute defenders of the steady-state theory, such as Fred Hoyle, continue to support increasingly unlikely ideas, only to face defeat in the face of overwhelming evidence. The proof presented was conclusive. It wasn't fading starlight or reflected heat from dust. The galactic glow showed a surprising consistency, resembling an ideal black body, but had no relationship with known objects in the universe. Despite this, Hoyle and his followers continued to subvert scientific progress by supporting scientifically unwarranted ideas. Meanwhile, the fields of space science and cosmology underwent massive advancements from the 1960s through the 2000s, with cosmology making especially remarkable strides. We mapped the universe, described its large-scale structure, and explored the evolution, advancement, and dynamic interactions of galaxies and their stellar populations. Yet, even with these advances, we encountered anomalies that challenged explanations within the framework of the Big Bang Theory, most notably the absence of predicted relics, such as magnetic monopoles or particles from grand unification. This led many to reconsider aspects of the theory. The universe we observe today seems to require forces beyond our current understanding. However, these forces remain elusive. At its origin, the universe required a precise rate of expansion to balance the overall energy density, something that the standard model of cosmology struggles to account for. This resulted in neither perfect harmony nor enough time for energy exchange across different regions of space. Given the immensity of the universe and its expansion over time, these anomalies present significant challenges to cosmology and mainstream scientists. The inflationary model and its challenges. While existing theories fail to account for observed abnormalities, two approaches arise: refine current theories or consider alternative explanations. The theory of inflation has emerged as the most promising framework for extending the Big Bang perspective. Inflation proposes a brief period of rapid expansion that smoothed the universe, presenting uniform properties. It addresses the horizon problem and predicts the development of quantum fluctuations, which manifest as density and temperature variations. The predictions of inflation align with observed patterns and fluctuations, supporting its validity, although alternative theories exist. Despite past contributions to general relativity and singularities, Roger Penrose's work, alongside his collaboration with Stephen Hawking, failed to match the progress of inflation in explaining the earliest moments of the universe. Recently, there has been deliberate work to undermine the validity of inflationary theory, pushing for formal cyclic cosmology. However, this theory is inherently flawed from a scientific perspective, as the key distinction lies in their predictions. Conformal cyclic cosmology suggests that remnants from a universe preceding the Big Bang are encoded in the cosmic microwave background and the large-scale structure of the universe. In contrast, inflationary theory maintains that the end of inflation and the hot Big Bang are causally separated from any pre-Big Bang era. James Webb Telescope's surprising revelations. Space researchers immediately noticed inconsistencies in the images sent by the James Webb Space Telescope beginning in 2022. These revelations may require a reassessment of key aspects of the universe's origins and evolution. One major discovery made by the Webb telescope was the presence of mature galaxies much earlier than expected by the standard cosmological model. This phenomenon challenges the established sequence of events following the Big Bang, where stars and black holes form first, followed by galaxies. Such revelations disrupt our understanding, much like encountering grandparents described as children in a story. Furthermore, recent evidence has uncovered inconsistencies within major theories of the universe, such as a persistent error in determining the Hubble constant, which continues despite improvements in data accuracy and collection methods. New data from Webb compounds existing challenges to the current cosmological model. These issues highlight flaws within the model, raising questions among scientists and physicists. While the model has undergone adjustments in recent years to align with emerging data, some argue that these changes have been too accommodating. As such, there is growing acknowledgement that a change in perspective might be necessary, potentially reshaping our understanding of the universe's fundamental properties. The standard model of cosmology, hailed as a triumph of human knowledge, emerged from Edwin Hubble's pivotal discovery of the expanding universe during the 1920s. Subsequent discoveries, such as the detection of the cosmic microwave background radiation in 1964, confirmed the theory of the hot Big Bang as the most viable explanation for the universe's origins. It portrayed the early universe as a hot, dense soup of subatomic particles steadily cooling over time. Rethinking cosmology, considering new evidence. Achieving the current level of accuracy in cosmological understanding has required theoretical extrapolation beyond observational data. The idea of continuous expansion, proposed in 1981, was introduced to resolve irregularities in earlier Big Bang models, further emphasizing the dynamic nature of cosmological theory. According to this model, the early universe underwent rapid, remarkable growth shortly after the Big Bang. While certain issues are resolved by this theory, new challenges arise, especially considering the prevailing belief in the existence of a single universe. Perhaps there are endless others beyond our observational reach. Several discernible anomalies, such as hypersingularities within black holes, find support through indirect evidence. However, the stunning revelations of the Webb Space Telescope regarding the formation of galaxies and the ongoing issues with the Hubble constant rays concerns that we may be approaching a tipping point. A significant overhaul of our current cosmological model may soon be necessary, potentially requiring a fundamental shift in how we perceive the universe's origins and evolution. This growing body of evidence from the James Webb Space Telescope, along with persistent anomalies in our current understanding of cosmology, suggests we are on the cusp of a major paradigm shift. As scientists continue to probe deeper into the universe's past and gather increasingly detailed data, the foundations of our cosmological theories may need to be reassessed or entirely rewritten. The Webb telescope's discoveries of mature galaxies appearing much earlier than predicted challenge the traditional sequence of cosmic evolution. These galaxies, with their unexpected complexity and size, imply that the processes of star and galaxy formation may have occurred differently or more rapidly than previously thought. This discovery alone suggests the need for new models that account for these early developments, which could alter our understanding of how galaxies form and evolve. Moreover, the detection of discrepancies in measurements, such as the Hubble constant, which is key to determining the rate of the universe's expansion, continues to puzzle scientists. These inconsistencies, where different measurement techniques yield different results, suggest that there may be unknown factors at play. The issue is not just a matter of refining observational methods. It could point to deeper, as yet unexplored aspects of the universe that could fundamentally alter our models of cosmic evolution. As we push the limits of technology and observation, it becomes increasingly clear that the universe is more complex than we once believed. Theories that have stood for decades, such as the standard model of cosmology based on the Big Bang, are being tested by new data that shows the cosmos may not be as simple as our current models suggest. From the formation of galaxies to the behavior of black holes and dark matter, scientists are confronted with evidence that challenges existing frameworks. In this context, we may be reaching a tipping point in cosmology where our understanding of the universe needs a significant overhaul. Some scientists are now advocating for a broader view of the cosmos that includes possibilities beyond the observable universe. The idea of a multiverse, where multiple universes could exist beyond our reach, is gaining traction among some theorists. While this concept remains speculative, the possibility that our universe may be just one of many in an infinite and dynamic multiverse opens up new avenues for exploration. Such radical shifts in perspective could require a reevaluation of the fundamental principles of physics, including gravity, quantum mechanics, and the nature of space-time itself. Just as the Copernican revolution reshaped our view of the Earth's place in the universe, or Einstein's theories transformed our understanding of space and time, the discoveries of the James Webb Space Telescope might lead to a new scientific revolution, one that could redefine our place in the cosmos. The growing realization that our current cosmological models might be incomplete or incorrect invites both excitement and uncertainty. As more data is collected and analyzed, we may discover that the universe is not only more complex than we imagined, but that it operates in ways we have yet to fully comprehend. The answers to these mysteries could dramatically change not only how we understand the origins of our universe, but also how we perceive the future of cosmology and our place in the vastness of space. In conclusion, the next phase of cosmological exploration, driven by instruments like the James Webb Space Telescope, promises to be one of immense discovery and transformation. With each new finding, We inch closer to unraveling the true nature of the universe, while also acknowledging that many of the questions we have asked may lead to even deeper, more profound mysteries. As we stand on the threshold of these new discoveries, one thing is